all about fluids, flames, and materials research aboard the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to StationLIFE.
Houston on 2 for velocity calculation. Go ahead and leave steps 4, 5, and 4, 6. We're moving on to
Tracy,
step
you
5.
want to go right now for that activity?
Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Welcome back. This month on StationLIFE, we're going to take a look at how the unique environment of space affects physical science experiments aboard the International Space Station. The ISS is a laboratory like no other here on Earth. Because of the lack of gravity, we can use it as a variable, or we can remove it from the equation entirely. It's this absence of gravity that allows us to observe the aspects of fundamental physics that we can't see here on Earth. Gravity here on Earth often masks or distorts subtle forces, such as surface tension or diffusion. On ISS, these forces can be harnessed for a wide variety of physical science applications. So in today's program, we're going to take a look at how the lack of gravity affects the physical sciences of fluids, flames, and materials. The ISS is an amazing place. It has all these laboratories and science racks to do amazing experiments that are literally out of this world. Come check it out.
The International Space Station is the largest, most complex object ever assembled in space and is clearly visible from Earth with nothing more than the naked eye. From end to end, the station is slightly longer than an American football field.
The biggest shock, I would say, the biggest impact that I had during my flight is the first time I looked out the window of the orbiter and saw the space station. It was huge. It was huge and shiny and beautiful. Looking at it and knowing that a man-made structure that big is actually up there.
The interior of this incredible structure is larger than a 5-bedroom house, with 2 baths, a gym, and a 360-degree bay window. The station's mass is almost 1 million pounds, and it contains about 32,000 cubic feet of living space. The space station functions as a microgravity and life sciences laboratory, a testbed for new technologies, and as a platform for both Earth and celestial observations. The complex is made up of multiple interconnected modules, grouped together at the center point of a 357-foot-long integrated truss structure. Power is generated through 4 giant solar arrays attached to the ends of the truss. The pressurized components include 3 laboratories: the U.S. laboratory module Destiny, the European Research Laboratory Columbus, and the Japanese experiment module Kibo. The Russian service module is the structural and functional center of the Russian segment of the station. It provides living quarters, communication systems, an exercise facility, and flight propulsion systems. Other Russian segments include the functional cargo block, 2 mini research modules, and a docking compartment. The Italian Space Agency provided a permanent multi-purpose module, which can host up to 16 additional racks containing equipment, experiments, and supplies. There are 3 modules called nodes that connect the elements of the station and provide berthing ports. The primary residential areas include the Russian service module and Node 3 Tranquility, which contains a bathroom for crew hygiene and exercise equipment, a treadmill, and a zero-G weightlifting device. The Quest airlock provides the capability for extravehicular activity, or EVAs. This is the module that provides the exit for spacewalking astronauts to go outside the station to work. The cupola is a small module designed for the observation of operations outside the space station. Similar to a bay window in a home on Earth, but with a 360-degree view, the cupola allows crew members to observe the approach of vehicles, as well as all robotic arm operations and spacewalks. The Canadian-built Space Station robotic arm is a larger version of the arm on the Space Shuttle and is used to move equipment and hardware around outside the station. The space station is the home of 6 full-time crew members and is made up of astronauts and cosmonauts from nations around the world. More than 200 people have visited so far, and at least another 120 will live there over the next decade.
I'm just getting my safety cutter on the other side of my IDA back here. Copy, Terry. A lot easier without the pool stanchion. Absolutely, yeah. And it's just like in the pool instead of that, the exception of that big planet down there. Exactly.
As the International Space Station flies 257 statute miles over the coast of Chile, Terry verts in the initial moments of his first spacewalk.
I don't know about you, but I like to start my day with an awesome cup of coffee. And on board the International Space Station, same thing, no different. But drinking coffee in space comes with its set of unique challenges. Without the pull of gravity, liquid acts in really strange ways. Even some of the most basic maneuvers, like drinking from a coffee cup, are confounded by the absence of the most fundamental forces we Earthlings take for granted. I mean, last time I lived on board the space station, we had to drink coffee out of one of these, a bag with a straw. One problem? There's no smell. You know, I find half the joy of drinking coffee is the aromatic bouquet as you drink it. So fellow astronaut Don Pettit came up with the solution and helped co-invent the first ever microgravity space coffee cup to enhance your coffee drinking experience on the ISS. So here's my good buddy Don Pettit explaining his ingenious, and that's more than genius, solution to the ISS coffee dilemma. I love that guy.
A normal coffee cup or a normal open container just simply won't work in a weightless environment because the liquid will be in the bottom of the cup and you tip it up and it still stays in the bottom of the cup. If you move it around too violently, it'll all splash out and make a big mess. So we end up having to drink our beverages through a straw from a bag. Makes you feel like you're a big insect sucking the juices from another insect. I wanted to see if I could figure out a way to have an open container cup in a weightless environment which would allow you to drink your tea and your coffee in a manner that's commensurate with how people drink their beverages on Earth. Taking some of my surface chemistry that I learned in college, I devised a cup with a special shape. The cross-section looks kind of like an airplane wing where it has a cusp, and the cusp will allow channel flow so the liquid from the bottom of the cup will float up and just park itself right next to the rim, and then you can drink it. And it allows a crew to share a communal beverage. You could share tea. Maybe you just come in from doing a spacewalk or something and you want to celebrate a little bit. If you have a real cup, an open container, it's so ingrained in human beings, it's so ingrained in culture, it adds back the dimension of what it's like to be a human being in a civilized way.
All kidding aside, the solution of drinking coffee in space, combined with the invention of the space coffee mug, have helped us better understand fluid properties in microgravity. So now let's take a look at how understanding the problems associated with drinking coffee in space relates to future space travel as well as life here on Earth.
High above our planet, in the realm of satellites and space stations, the familiar rules of Earth do not apply. The midday sky is as black as night. There is no up and no down. Dropped objects don't fall, and hot air doesn't rise. Of all the strange things that happen up there, however, it is possible that the strangest happens to coffee. In microgravity, a simple morning cup of joe can be an out-of-this-world experience. Physics professor Mark Weislogel of Portland State University has given a lot of thought to coffee and other fluids in space, and he describes what happens. For starters, he says, it would be a chore just getting the coffee into the cup. Absent the pull of gravity, pouring liquids can be very tricky. But for the sake of argument, let's suppose you are on the space station and you have a cup of coffee in your hand. The most natural thing would be to tip the cup toward your lips. But when you do, the coffee would be very hard to control. In fact, it probably wouldn't move. You'd have to shake the cup toward your face and hope that some of the hot liquid breaks loose and floats towards your mouth. On the bright side, you will probably be wide awake by the time the cup is empty. Coffee is not the only liquid that misbehaves in space. Cryogenic fuels, thermal coolants, potable water, and urine do it too. The behavior of fluids is one of the most unintuitive things in all of spaceflight. This poses an extreme challenge for engineers designing spacecraft systems that use fluids. Our intuition is all wrong, laments Weislogel. When it comes to guessing what fluids will do in new systems, we're often in the dark. To develop a better understanding of fluids in microgravity, Weislogel and colleagues are conducting the capillary flow experiment on board the International Space Station. For instance, one of the devices in their experiment suite looks at interior corners. If two solid surfaces meet at a narrow enough angle, fluids in microgravity naturally flow along the joint. No pumping required. This capillary effect could be used to guide all kinds of fluids through spacecraft, from cryogenic fuel to recycled wastewater. Capillary-driven flow is difficult to study on Earth, where it is dampened by gravity. Yet on the space station, large-scale corner flows are easy to create and observe. Weislogel and colleagues have already been granted 3 patents for devices invented as a result of their work. One is for a microgravity condensing heat exchanger. Another describes a device that separates and controls multi-phase fluids. The third patent is for, you guessed it, a low-gravity coffee cup. Astronaut Don Pettit, who worked with the capillary flow experiment during his time on board the space station, helped invent the cup, and he shares the patent with Weislogel and 2 mathematicians, Paul Konkis and Robert Finn, who performed the first theoretical analysis of the phenomenon. Basically, one side of the cup has a sharp interior corner. In the microgravity environment of the space station, capillary forces send fluid flowing along the channel right into the lips of the drinker. As you sip, more fluid keeps coming, and you can enjoy your coffee in a weightless environment, clear down to the last drop, says Pettit. This may well be what future space colonists use when they want to have a celebration. Indeed, the patent application specifically mentions toasting as one of the uses of the device. It's easy to imagine what they might be toasting. Toilets and air conditioners and fuel tanks and recycling systems, all working better thanks to capillary flow experiments on the space station.
Avalon 2 for any available USOS crew member. No response required, but if you could please close the lab shutter. Thanks.
As you can see, the study of how the microgravity of space affects fluid physics is fundamental to the future of space travel. Things get even a little more crazy when we start to look at how the microgravity of space affects the fundamental properties of the very fire we use to heat our coffee. Here on Earth and in our everyday lives, we understand how fire behaves. There's very few surprises. But in space, completely different story. On ISS, we can use it as an opportunity to study the fundamentals of fire so we can better understand it. So let's take a closer look at this phenomenon. Fire, it is often said, is mankind's oldest chemistry experiment. For thousands of years, people have been mixing the oxygen-rich air of the Earth with an almost endless variety of fuels to produce a hot, luminous flame. There's an arc of learning about combustion that stretches from the earliest campfires of primitive humans to the most advanced automobiles racing down the superhighways of the 21st century. Engineers studying burning to produce better internal combustion engines. Chemists peer into flames looking for exotic reactions. Chefs experiment with fire to cook better food. You would think there's not much more to learn. When it comes to fire, flames are hard to understand because they're complicated. In an ordinary candle flame, thousands of chemical reactions take place. Hydrocarbon molecules from the wick are vaporized and cracked apart by heat. They combine with oxygen to produce light, heat, carbon dioxide, and water. Some of the hydrocarbon fragments form ring-shaped molecules called polycyclic aromatic hydrocarbons, and eventually soot. Soot particles can themselves burn or simply drift away as smoke. The familiar teardrop shape of the flame is an effect caused by gravity. Hot air rises and draws fresh, cool air behind it. This is called buoyancy and is what makes the flame shoot up and flicker. But what happens when you light a candle, say on the International Space Station? In microgravity, flames burn differently. They form little spheres. Space station flame balls turn out to be wonderful mini labs for combustion research. Unlike flames on Earth, which expand greedily when they need more fuel, flame balls let the oxygen come to them. Oxygen and fuel combine in a narrow zone at the surface of the sphere, not here and there throughout the flame. It's a much simpler system. Recently, on a space station experiment called FLEX, where scientists learned how to put out fires in microgravity, they noticed small droplets of heptane were burning inside the FLEX combustion chamber. As planned, the flames went out, but unexpectedly, the droplets of fuel continued burning. The flames are there, just too faint to see. These are cool flames. Ordinarily, visible fires burn at a high temperature between 2200 and 3100 degrees Fahrenheit. Heptane flame balls on the space station started out in this hot fire regime. But as the flame balls cooled and began to go out, a different kind of burning took over. Cool flames burn at the relatively low temperature of 400 to 1000 degrees Fahrenheit, and their chemistry is completely different. Normal flames produce soot, carbon dioxide, and water. Cool flames produce carbon monoxide and formaldehyde. Similar cool flames have been produced on Earth, but they flicker out almost immediately. On the space station, however, cool flames can burn for nearly a minute. There are practical implications of these results. For instance, they could lead to cleaner auto ignitions. One of the ideas that auto companies have worked on for years is HCCI, short for homogeneous charge compression ignition. In the automobile cylinder, instead of a spark, there would be a gentler, less polluting combustion process throughout the entire chamber. The chemistry of HCCI involves cool flame chemistry. The extra control we get from the steady state burning on the space station will give us more accurate chemistry values for this type of research.
The Combustion Integrated Rack, or CIR, in the Destiny Laboratory makes it possible to perform a wide variety of experiments that teach us how fire behaves in microgravity. In the center of the CIR is a large round chamber called the Multi-User Droplet Combustion Apparatus. The 100-liter chamber has 8 windows and 5 cameras that allow scientists to observe patterns made when burning fuels under different conditions. The 5 cameras are capable of photographing high-resolution, high frame rate images in ultraviolet, low light, and in multiple spectrums that are specific to combustion events. Several additional hardware components can be added to the SIR to customize its chamber for specific experiments. FLEX is the flame extinguishment experiment that utilizes the SIR to conduct various burn tests on gas and liquid fuel. It also tests the effectiveness of different methods for extinguishing the flames from the test. ISS provides a sustained microgravity environment, which allows scientists to observe the geometric, chemical, and thermodynamic properties of both the flame and the fuel droplet inside the burn chamber. Under these conditions, we can advance our fundamental understanding about how fuels burn in microgravity as well as on Earth. This research will be used to better address fire hazards associated with liquid combustibles. The wealth of information obtained from the test in FLEX will also help scientists on Earth solve problems with pollution that are generated by combustion. The many different experiments in the Combustion Integrated Rack will help engineers increase the efficiency of gasoline and diesel engines here on Earth, and will help us understand fire prevention and suppression.
I'm looking for a little bag called the Component Repair Expedition Along Toolkit. It is not find it in the bag listed in the location, but I did find it in the same block in 1/2 CTB 1204. And we'll check on that given.
Now that was hot. Okay, fluids and flames are acting a little differently. But that's not all. Let's take a look now at colloids, magnetic fluids, and smart materials. But first let me tell you what those are. Colloids are fluids that contain suspended particles. Magnetic fluids are smart fluids that increase in apparent thickness when exposed to a magnetic field. And smart materials are specially designed to significantly change in a controlled fashion when exposed to stress, temperature, or a magnetic field. Colloids, magnetic fluids, and smart materials, oh my! Now let's take a look at how these are studied on ISS. If you have a smartphone, take it out and run your fingers along the glass surface. It's cool to the touch, incredibly thin and strong, and almost impervious to scratching. You're now in contact with a smart material. Smart materials don't occur naturally. Instead, they're designed by engineers working at the molecular level to produce substances made to order for futuristic applications. The Corning Gorilla Glass that overlays the displays of many smartphones is a great example. It gets its toughness in part from fat potassium ions stuffed into the empty spaces between old-fashioned glass molecules. When the molten glass cools during manufacturing, dense packed molecules solidify into a transparent armor that gives Gorilla Glass its extraordinary properties. Around the world, designers are working on other smart materials, such as alloys that can change shape on demand, plastics that heal themselves when ruptured, and fluids that obey magnetic commands to flow or stiffen under computer control. One of the greatest challenges in creating a smart material is arranging the molecules. They're so small. We want to create a new class of materials beyond smart. We need genius materials, materials that arrange themselves. The research to accomplish this is already underway on the International Space Station. Dr. First is the principal investigator of an experiment called In-Space 3. In the microgravity of Earth orbit, vials of fluid mixed with very small colloidal particles, about 1/millionth of a meter in diameter, are exposed to magnetic fields. Magnetism can be switched on and off again very rapidly. This jostles the particles, causing them to bump together and self-assemble into microscopic structures. These structures can be very difficult to predict, even using cutting-edge models running on supercomputers. Astronauts enjoy watching this process in action through microscopes. Because the samples are backlit by a green lamp, they sometimes call it the green blob experiment. First recently won an award from the American Astronautical Society for his work on In-Space 3. Just by toggling a magnetic field, we're learning how to take many kinds of microscopic building blocks and get them to spontaneously form interesting structures. Recently, observers have seen the colloidal particles forming long fibrous chains.
first speculates that these could lead to materials that conduct heat or electricity in only one direction. The experiment has also yielded crystalline structures that the team is just beginning to investigate. The fluids underlying these tests are themselves very smart. They're called magnetorheological, or MR fluids, because they harden or change shape when they feel a magnetic field. If you own a sports or luxury car, you might have MR fluids in your shock absorbers. The stiffness of magnetic shocks can be electronically adjusted thousands of times per second, providing a remarkably smooth ride. Similar but more powerful devices have been installed at Japan's National Museum of Emerging Science and China's Dongting Lake Bridge. They're there to counteract vibrations caused by earthquakes and gusts of wind. Some researchers have speculated that MR fluids might one day flow through the actuators and hydraulic dampers of robots, moving artificial joints and limbs in lifelike fashion. Scientists and researchers are using these fluids as a laboratory for studying self-assembly. MR fluids are, by definition, responsive to the magnetic nudging that sets self-assembly in motion. Furthermore, in space, the particles don't sediment out due to gravity. We can study the full 3D evolution of the material. Varying the shape of the colloidal particles, the cadence of magnetic toggling, the temperature of the fluid, and other factors will allow researchers and astronauts to further explore the frontiers of self-assembly. Touch the surface of your smartphone again. That's just the beginning.
The International Space Station is an unprecedented research platform in space, allowing scientists and researchers from all over the world to conduct experiments that can't be done anywhere else. This work off the Earth will lead to a better understanding of the fundamentals of surface tension, combustion, and colloids in the absence of gravity, benefiting us by helping to make more efficient combustion engines, better portable medical diagnostics, stronger, lighter alloys, medicines that have a longer shelf life, and buildings that are more resistant to earthquakes. Research on the International Space Station continues to benefit us all here on Earth. Be sure to stay in touch and follow us on Facebook and Twitter for the latest research news. And don't forget to download our newest app on your mobile device. Until next time, we're working off the Earth for the Earth.